Thank you for the intro. Thank you also to all my co-authors, Youngkam, Stefan, Magnus, and Andre, without whom I couldn't do this. This talk is going to be all about cyber-physical systems. Many of these are safety-critical systems ranging from airplanes to pacemakers to self-driving cars, you name it. But I know you guys have been here all week, so I'm trying to keep it a little bit of a lighthearted, fun talk. So I'm going to start off with a different system, one of my favorites. Okay, this is a robot. His name is Method 2. He's 13 feet tall. He could reach to the top of that projector. And he weighs about 3,000 pounds, so about as much as everyone in the front row put together if people were indeed, sitting in the front row. Okay, and this guy scares me, okay? He doesn't just scare me because he looks like he wants to step on me. No, he scares me for another reason, right? He scares me because he's running a large amount of low-level code. His control software is maybe, millions and millions of assembly instructions. And this stuff is very hard to get right or to show to be correct. And not only do you need to know the code is correct, but you need to understand how it interacts with physics. You need to understand how this interacts with all of his actuators that he uses to control the world around him, as well as all his sensors that he uses to perceive his physical environment. So what are we going to do to make sure this robot's correct, or to make sure a plane or self-driving car or any other one of these cyber-physical systems is correct? First thing I'm going to do is I'm going to put him in a box over here. And then I'm going to call this box reality, and I'm going to get as far away from reality as I know how. When I do, I'm going to get to the current state of the art in cyber-physical systems verification. This is what we call hybrid systems theorem proving. Hybrid systems are high-level mathematical models that you can use for these cyber-physical systems. They talk about discrete transitions, which allow you to model control software, as well as continuous transitions, which allow you to model physics. Okay, there's a logic called differential dynamic logic, which I'll use throughout the talk, that you can use to model and verify these. And there's a theorem prover developed by our group called Chimera X, in which you can do these proofs formally. Okay, and it's been applied successfully to a number of domains, but there's still a problem, right? There's this big white blank space in the middle of the slide, and this is the gap between your high-level models and the low-level implementation. What I really want is to know that the implementation is safe. And what I would really, really like is for me and all of you to be able to work at a high level in this modeling language and have someone else just figure out how to take our safety theorems and transport them all the way to the other side, transport them automatically to something I can actually run. And that's what this talk is all about. So VeriPhy is a tool that we built that takes as its input a high-level verified hybrid model of the system. And it performs a series of transformations with proof that extracts software you can actually put on the robot and run. The way that software works is not by trying to verify every one of those million lines of low-level code. It works by a verified sandboxing monitoring approach. So you simply ask the control software, what decision do you want to make? And if you think it's about to do something potentially unsafe, you replace it with a simple verified fallback action. Okay, I'm going to go through all of this in a lot more detail. I'm just setting it up right now. But the starting point is you need to start with a good model. So the model describes not just one specific controller implementation, but all possible safe behaviors. From that, we can extract monitoring conditions that tell you whether the untrusted components are behaving correctly. From that, we implement all the real numbers that are in our source model soundly using discrete arithmetic. From there, we generate code, which is then compiled with a verified compiler all the way to machine level. And then when we take that code, we can, of course, put it on hardware and actually run it. Now, this guy was a little bit expensive. He cost something like 1 billion won, so we couldn't buy him. We bought this robot instead. This is a cute little Raspberry Pi bot, and we, in fact, ran our code on him. We saw that it worked pretty well. And we're going to talk to you about what we learned when we ran stuff on this robot. Okay? And why did it work so well? Well, I like to think, again, because we have this chain of safety proofs. So the initial model at the input stage has to be provided with a proof of some safety theorem. Safety theorem is also provided by the user. Typically, for something like a robot, this would just say, I'm not hitting other robots, I'm not hitting walls, etc. Okay? From there, every transformation stage, the monitor construction, the arithmetic implementation, the compilation are all verified in the theorem prover. Okay? You might wonder, what is the theorem prover that we used? So we actually used a few different theorem provers for different stages. Okay, so we have our own theorem prover, Chimera X, that you use for the initial input model. The arithmetic stages are in Isabelle, and all the compilation stuff is in Hall 4. Okay, this might not be the only approach, but there's a good reason we took this approach, which is simply that we needed a lot of different features throughout this project. So at the high level, we wanted all this invariant generation and variant proving technology that comes from the dynamical systems community. At the other end, we wanted to be able to compile this and compile from a high-level language, do so with proof easily. And in the middle, we needed good analysis libraries. Okay? Not only that, we even did do some work to help try and connect these provers in the best way possible. Okay? There's also some future work that you and the community will be able to help out with that going forward. But I just wanted to mention it. And now, that's the introduction. So now we're just going to take a leisurely walk one step at a time through all the steps of this transformation process, starting from a verified safe model down to an executable. All right, let's start with the source model. This is a hybrid systems model written in a syntax called hybrid programs. This is simply a hybrid system in program notation. And what this model does, this is the one that we ran on our little robot. It's a one-dimensional model saying I'm moving in a line, I can control my velocity, and I'm trying to avoid some obstacles, say a wall. The first thing the model does is it asks how far am I from whatever obstacle I'm trying to avoid. If I'm far enough that I don't think I'm about to hit it, then I can set any velocity within the physical capacity of the robot. When I said that we need to consider all possible safe behaviors, this is what I mean. We're not saying exactly how to compute that velocity, we're just saying that any velocity you might choose in this range are all going to be safe. Now, if we are getting too close, we have another case that says simply set the velocity to 0. This is also going to be used if those untrusted software components are trying to do something that we say is not allowed by the model. We'll use this as a fallback to say we always have a proven safe default option if the untrusted components are trying to do something inherently dangerous. Regardless of which control decision you make, the robot is then, of course, going to actually move. This is modeled as a differential equation. D is just the distance between the robot and its obstacle, and we say that that moves according to its velocity, right? But it doesn't do this forever. It does it up to some time step epsilon. So we have some time-triggered control, and every time epsilon, the controller gets to run again. If you don't have something like this, it's, of course, it's not realistic to have this code that runs in 0 time. Now, you may even think this model's a little bit simple. But actually, as we'll see when we run this on the robot, it's nice to start with a simple model because we can validate this model by running it and figure out when these simplifications are valid or when we need a more complex model. Okay, once you have that model, the other input you need to give our system is you need to actually prove that this thing is safe. You're going to do this using the Chimera X theorem prover developed by our group. That screenshot in the middle is a screenshot of the prover. In addition to feeding in the model, you feed in a few other things. For a simple model like this one, you can get away with just feeding in invariant informations for your system loop and for your differential equations, and it can take the proof from there. As your models get more complicated, you might want to pull out your keyboard and write a tactic script that programmatically does the proof, or you might want to pull out your mouse and click around in the UI and do it step by step, which we think is especially good for when you're learning the system. On the other side, what you're going to get out, obviously, is the fact that your theorem is actually true. Again, theorems might be something like, if I ever reach my obstacle, I do so with velocity 0, or maybe I never hit my obstacle. But you're also going to get these monitoring conditions as an output of the prover, telling you whether the untrusted components are doing what they're supposed to. And everything we discuss from this stage forward is all going to be outputs that we produce for you automatically. And one of the side pieces of work that we did during this project, you can even get a proof term that allows your proof to be cross-checked in Isabelle Hall. This gives us a very strong foundation, and on the bottom you can see everything that's in the foundation of this prover. There's a few different pieces, but at each point there's never a single point of failure. So there's different choices you can use for how to trust the core, and there's different external solvers you can choose between trusting. Okay, let's zoom in on those monitoring conditions. There's actually going to be 2 things that we monitor, and both of these will be synthesized for you. So the first thing, again, is we check whether the control software fits the assumptions on what the model says you can do in your control. That's what this red line is doing. And this particular red line is within the safe envelope, meaning that the control suggested something that was actually safe according to the model. In this case, the monitor will go ahead and run that. The other thing that could happen is your control could try to tell you to do something that isn't actually safe or isn't proven safe. In this case, you're going to reject it, and we're going to automatically do whatever your model said was our backup option. In this case, we just say, put on the brakes, have the robot stop right now, which is safe. Okay? We're also going to monitor the sensors. So we're going to monitor the physical part of the system. What we can do is every time we read from the sensors, we can check, is this consistent with my model of how physics actually works? Is this consistent with the idea that I'm directly controlling my velocity? And so when we test this, we can see when this goes off, and we can see when this model is appropriate and when it's not. When this ever goes off, you can't actually guarantee perfect safety, right? If the laws of physics are broken, you're doomed, right? If I start falling up, there's nothing I can do. But we can still do the fallback control. This is going to be much safer than doing nothing, and it's extremely helpful during the development process because it gives you early evaluation of whether your assumptions are reasonable. Okay, we can take these formulas, and within this hybrid program language, we're going to build a model that incorporates both that untrusted control and that verified fallback. So in the yellow, okay, here's the template, here's the instance for the one-dimensional robot. In the yellow, I'm reading in from the untrusted controller. In the red, I'm checking whether that fits my modeling assumptions. If it doesn't, I run the green fallback control. Regardless, once I reach my sensors, I'm going to check whether those sensors are consistent with my physical assumptions. Now, I might not sound excited, but we should be excited right now because this is the thing we want to actually compile and run. The rest of this pipeline is just about how we're actually going to compile this down to machine code and how we're going to do so safely. Okay? And a correctness proof, safety proof, is synthesized for this along with the program. Now, I'm going to zoom in on just one part of how we implement real arithmetic. Now, I hope everyone in this room can tell me which number is bigger, pi or e, right? This is a known problem, but computers aren't so smart, so if we want to even compare two real numbers, we need to be pretty careful. And what we're going to do is a very simple approach. We're just going to wrap each of these in an integer-valued interval. We're going to say pi is somewhere between 3 and 4. E is somewhere between 2 and 3. And we can compare these intervals. Pi is definitely no smaller than e. You can see that from the diagram, right? But pi is definitely smaller than, say, e plus 3. The case where it gets tricky, of course, is if you're saying pi versus e plus 1, because when you compute with these are going to be represented by the same interval, even though they're different numbers. And all this is showing is that this has to be conservative. If these intervals overlap, we can't know which one's actually bigger, and this is a known unknown. When you have a known unknown, the entire logic is going to become a three-valued logic. This percolates everywhere. Okay? Specifically, we used a Wilkersevitz-style three-valued logic. You can define conjunction, disjunction, all the other connectives. You can define arithmetic by saying when you work with the lower bounds, you round downward. When you work with your upper bounds, you round up, that sort of thing. You can even define how programs work. And again, when you compare two terms, you just say a value's unknown if the intervals ever overlap. Once we defined the semantics, we then went to the Isabelle Hall prover, and we actually proved that this is sound with respect to the source semantics, okay, the model that we actually verified in Chimera X. What this theorem just says is that if the interval semantics ever believes something's definitely true or definitely false, it's going to actually be true or false at the source level. In the case where it overlaps, again, we're not making any claims. But by proving this theorem, we've connected from this easier-to-compute interval language back to our source model. Okay, here's that sandbox program again. This is what we want to compile, and we just figured out how to compute with the real numbers. But we still need to get this all the way down to machine code, and I haven't told you how to run this language. Now, the approach we took is to compile this to another language. And we actually chose to use the KML language in toolchain because it's quite close to the language we're working with, and it's something we understand very well. You'll notice there's a lot more yellow on this slide than the slide before. Yellow represents everything that's external to our program, everything that's implemented through foreign function interfaces. You'll notice there's a lot more, and what this means is this was the stage of the pipeline where we actually spec'd out what we expect the real world to look like, how it's supposed to behave, and what are the assumptions on how the sensors and actuators inform us about the real world. That's all in the paper, but I just think it's fun to model things about reality. Okay, we have a theorem that also relates this back to the interval semantics. There's a few cases, so this is just the simplest case, but simply it says anytime you have a transition in your KML level program, that transition also exists in the world of interval semantics. And this allows us to link from executable code back to the interval model, which by composition links us all the way back to the model we started with. We're almost done. You can almost run this thing, I promise. So we take the ML source, we stick it in the KML compiler, and you get out an object file. Congrats! You can now mix this with your implementation for external control, sensing, actuation, all that. This might be written in C, it might be written in whatever language you want as long as it follows that sort of C foreign function interface. You link these together and you have an executable. I don't know about you, but I know what I do whenever I get a new executable, right? I execute it. So we ran this both on a simulation and we ran it on an actual robot. And these plots are just showing what is the robot's position over time. You don't need to read every detail. I'm just going to tell you some of the questions we were trying to answer with this. The first question we wanted to answer is how operationally suitable are these monitors? So if your monitor is constantly telling you that everything is dangerous, right, that you need to stop your robot all the time to be safe, then that's not a useful monitor. We want a robot that actually drives around, actually interacts with the world, right? And if you look at the little lightning bolts that some of these have, that represents the cases where these alarms went off. And all of these went off in situations where we had a really good reason. Most of these are from when we intentionally used either an adversarial controller that says go full speed ahead all the time, or when we had an adversarial environment. Adversarial environment meaning something like I picked up an obstacle and I just literally waved it in front of our robot's face and told it, the wall is running at you. And I don't know if it's even on this slide, sorry. I don't know if it's on the slide or not, but there's a couple cases where as you get very close to the wall, there were a few that actually went off because that differential equation was so simple. And so on the one hand, we were pretty excited to see that even with this simple model, this physical monitor barely ever went off. But at the same time, it does allow you to see the few cases where that model is too simple. And this helps you if you're designing a model and you want to iterate, and you want to know, is my model need to get more complicated, or can I get away with doing things very simply? We also use this as a way to evaluate our arithmetic implementation. Okay, so when we ran our arithmetic, we actually did not see any false alarms arising from this conservativeness. And we also saw that we didn't even use the full range that was available to us. So we used about 20 bits of precision is enough to get a pretty good precision on the sensors that we were using. Although you can imagine having other systems where you want higher precision arithmetic. Okay, we're getting close to the end, so I just want to start wrapping up. So why was this guy safe? And why is it that we can claim an end-to-end safety theorem when so many people have tried to verify cyber-physical systems before and done all this great work, and they never said it was end-to-end? The way I like to think about it is it's because we take a semantic approach, or you could even say, being PLDI, that we take a language-level approach. So when you model your system and when you plug it into the theorem prover, we actually know mathematically what it means to be a hybrid system, right? We know what it means to prove that's safe. And we know what it means when we do this language level transformation that turns the arithmetic into the simpler interval arithmetic that we know how to compute with. We translate it to ML. All these are language transformations that are well understood. And by composing them together, we can say that the semantics of our machine code level program soundly implements what we started with in the beginning. All right, we're getting to the end now. I just want to leave you with a little bit of a takeaway metaphor. And again, I wanted to give you a little bit of fun for one of the last sessions of PLDI. So what did we really build? We built Super Mario for proofs. What I mean by that is that we already had models that have been proven safe. We know how to model and prove things about our models. But what we've really wanted all along, the goal of cyber-physical systems verification, is to make real systems actually safe in practice. There's many obstacles to that. It's a very hard problem. It's not, you're never going to solve it in one day. But one of the obstacles is this massive proof effort that you would have if you took that massive pile of control code and tried to manually verify every single instruction at a low level. So we did what any good plumber would do. We built a pipe. And you can send your model in one end of the pipeline, run some code, and what it'll give you on the other end is executable monitor code that you can actually run and that actually has a chain of safety proof supporting it. If you'd like to learn more, we've got this website, verify.org. And I'd really love to talk to anyone either who has a model they've verified and they want to actually learn how to run things on real hardware, or anyone who has a hardware platform that they want to work with and want someone to collaborate and provide them with a model that's actually proven safe. Thank you.
We have time for a few questions.
Great work. So I have a question about your interval arithmetic.
Yes.
So does this mean that your regular controller is still running using standard floating point number representation? It's just your monitor is using these intervals representations? Or?
Yes, so it can use whatever kind of arithmetic it wants. At some point, it's going to feed information to the monitor so we can check whether the output is correct. So it would sort of cast its result into the interval language when we do the monitor check.
I see. And does it actually give you better performance or worse, or
So since the monitors are so simple, we actually haven't really had any performance issues. They're usually just some little formula that you write down. I think performance is one of the advantages of it, and also just one reason we chose this is because it's so widely used and so well understood by the embedded systems community, the people that would be building this side of it. So aerospace, for example, this kind of integer or fixed point arithmetic is prevalent.
I see. And what level of precision you need to get to, because these interval,
right?
I mean, integer intervals, right?
Yes.
Presumably
So
it has
I say integer, but sort of the reason that this still actually works is you can set the physical units to whatever you want. So I say integer, but our sensor was reading, integers in microns or whatever, or maybe integers in millimeters. So you could also effectively think of it as being a fixed point arithmetic.
And you have some library package help you compare these integer intervals with the actual IEEE
Yes,
floating point numbers.
Right, so there's other people have made this kind of library before, but because we wanted to have it all verified and we wanted to be able to use this source language that we started with, we implemented these interval things ourselves and we proved them ourselves in Isabelle Hall. You can imagine trying to fit in other libraries if you wanted to.
So you have used several different theorem provers
Yes.
In this process. Can you say something about how you connect those proofs together?
Yes, so there's two connections in the pipeline. One of them is already in really good shape. The other one I would like to think of as a sort of call to the broader community, especially the interactive theorem proving community, to figure out how we can make these connections better. So going from Chimera X to Isabelle, we can actually spit out a proof term, and I have an Isabelle proof that proves the core of Chimera X sound, and we generated code from that, and you can actually run your proof term again in the proof checker that I generated that was proven sound. So that's a very strong connection. But going from Isabelle to Hall 4, basically the best we know how to do right now is just translate some things by hand. There are tools out there that try to get this automatically, like OpenTheory, but OpenTheory is actually currently still working on getting a better connection because there's some features that KML needs that they don't quite support. There's also better verified code extraction that people are working on that could get some of these proofs from Isabelle down verified in a nice way.
So do you get a final theorem about all these transformations in the end in your paper, or you're still working on it?
So the final theorem is in the paper, right? In some sense, the final theorem is a paper theorem because if you're composing between different provers, then you don't get a theorem, you don't get a statement in one prover at the end. But simply what it says is that when you're running the actual system, then the short story is that the state that you have in your code corresponds to a real physical state, and since that real physical state appeared in your source model, then it's the state that was proven safe. It was one that meets the post condition that you have.
Okay. Yeah. Thank you.
Yep.
Maybe the next speaker can get set up while we take the last question.
Suppose your unverified controller code contains a bug, maybe a vulnerability. Can it compromise what the trusted monitor does? And do you address this?
So it depends on where your vulnerabilities are. So if there's a vulnerability in your sensor and someone's feeding you totally bogus information where you are, that kind of thing, we don't know how to deal with that. At the other hand, if someone hacks just the untrusted part and makes it give a bad answer to the monitoring software, that's what the monitor is for. That looks the same from our perspective as if someone had just written a buggy controller instead of one that was compromised.
I was actually hinting at something yet different, namely if there's a code execution vulnerability which allows you to put the program counter somewhere else.
We don't do anything about code injection kind of attacks.
Okay.
Yeah.
Okay, let's thank Brandon again.